All right, so I found out sadly that we don't read the classics in high school anymore. Nobody reads Charles Dickens? Oh, you got it. That's what it's about. Tale of Two Asses. It's supposed to be a tale of two cities. You ever heard it? The preamble was the best of times, it was the worst of times, like the age of raise the age, all that. So I came up with, it was the strongest of acids. It was the weakest of acids. It was the fully ionized, and it was only the partial ionized.
It was the age of wisdom, it was the age of foolishness.
There it is. Let's do a little foolishness. So what I plan to do is show you, side by side, the difference in how we solve problems related to solutions that are made with strong acids, which I've listed here for your convenience, and weak acids. The primary difference is that the strong acid problems are just going to be some kind of stoichiometric stuff and the pH equations. In other words, if I give you the molarity, you just plug it in, because it's the same as the molarity of the hydrogen. If I give you the mass and the volume, you have to find moles and molarity and then plug it in. That's the only thing. So these are like the easy ones. Allow me to demonstrate. So the question I'm going to answer on this side is, what is the pH of a 0.1 molar HCl solution? So again, the goal here is, based on how much acid is in the water, we should be able to figure this out. So I'm going to write it out in gory detail for you, even though you probably won't need to do this way again, because it's going to be pretty obvious what's up there. But first, let me also remind you that the equations we're writing, where we show the acid or the base reacting with water, is called hydrolysis, which literally means reacting with water. So I'm going to write the equation as HCl. One of these has to work. So hydrochloric acid, which is aqueous. You put it into water, which is liquid. One-way arrow, because this is going to go 100% to ions. It's strong. And that's what makes these easier. You get the hydronium, and then you get the conjugate base chloride. So what we know is that we're starting with 0.1 molar of this one. The liquid water amount is going to be effectively constant because it's so much more than everything else in the system. So we don't have to worry about that anyway. But we're going to lose, we're starting with effectively 0 of each of these. So we're going to lose X here and gain X here and here. Now, the difference is, if it's a strong acid, X is the whole thing. So really what's happening in this case is we don't even need X. All of this breaks down. So none of it is left in the molecular form. That means this is increasing also by 0.1. And so is this. So well, it's not even equilibrium, but at the end of the reaction, we have 0.1 molar concentration of hydronium. And that's all we really need to find the pH, because the pH is right here. We just plug it now into the pH equation. So from here, to get the pH, we would just write negative log of 0.1, and of course mathematically that equals 1. So when we're working with a strong acid, and I'll make a similar argument later for strong bases, it's just stoichiometric, because every molecule that can deliver a hydrogen does. So whatever your concentration of the strong acid is, same as the concentration of hydronium you get. Once you know that, you can find the pH. Any questions? What? The questions are there? Oh, someone. Okay. Now, how does it look different if we were doing a weak acid? Well, let's find one that's really similar to that one, so it looks almost identical in every way. In fact, what's interesting here is that hydrochloric acid is one of the 3 in the same family of strong acids, but one that's suspiciously missing is chlorine. So it turns out hydrofluoric acid is a weak acid. So if you start here, the first thing I'm going to do is ask the same exact question. What is the pH of a 0.1 molar hydrofluoric acid solution. So my first instinct might be, oh, it's got to be the same. I get one hydro, blah, blah, blah. But it's not going to be the same because not all the molecules give up their hydrogen. So writing the hydrolysis reaction first, just like before. Now remember, whether or not this turns into ions, it's still in solution, okay? Even if it doesn't break down. Now I use the double arrow because I'm looking at an equilibrium process. It's not going all the way. But other than that, this looks very similar to what I did on the other side. Here's one of the big differences. We can't solve this problem without one more important piece of information, the equilibrium constant, which we label Ka. A couple notes about Ka, which I'll put above here just for space-saving purposes. Ka is equal to the acid dissociation constant. It's a measure of how strong the acid is. Because if you look at this equilibrium, the bigger Ka gets, the more we lean toward the products. And the more we lean toward the products, the more hydronium will be in the water. So that's what that does. And just like any other equilibrium process, we can write an expression for it using the rules we've already learned. It's going to be, in this case, the hydronium concentration times the fluoride concentration all over the molecular form of the acid in the denominator, right? We're just following the same rules we did. We left out the water because it's a pure liquid. But that's essentially what we know. Now, we need a value for it. So lucky for you guys, somebody took the time, not me, to assemble tables of these values, so when we need them, we can call them up. And show you where you can find that on my resources for now. Maybe. Kick the table out. Wire. Anyway, to show you where those resources are on our side, eventually when the thing actually decides to work. Come back. Computers. There's a link right in the syllabus today that says Ka table. So let me open it and show you what's in there and how we're going to use it. So over here, when I open it, you'll see lists of different acids. I also have the bases at the bottom that are important, but for now, we have to find that specific acid on this table. Hydrofluoric acid has KSP, sorry, Ka 7.2 times 10 to the minus 4. So for this one, our Ka is equal to 7.2 times 10 to the minus 4. Now if you think about it, to get to the pH, we need to know how much hydronium is in the water. But that's something we can answer with a simple ice table. Because we know we're starting with 0.1 molar of the hydrofluoric acid. The water isn't really going to change. It's not going to matter to us here. The hydronium, we assume, starts at 0, 0 here. And then we can see X of this is going to go, creating X of each of these. So at equilibrium, we'll have 0.1 minus X, and then X, and X. Again, it should look identical to all the equilibrium jump we can do. So now I just have to plug in my expression in terms of X and solve. So in this case, I'll go up here so I can see a little better. Now, this is not very hard to solve analytically, meaning we can use the solver. We could probably do the quadratic easily by hand. But once again, we're going to take advantage of that assumption that X is going to be too small to matter. Will that always be true? In real world, no. On the AP exam, I'm pretty sure it is. Meaning that you're probably going to be able to make the simplifying assumption that we've been making during the KSP. So I'm going to actually solve it both ways and tell you kind of a rule of thumb we use to see if it's valid. And then you can judge for yourselves. But let's start from the assumption that this is small enough to ignore. So if we cross this off, now we just multiply over and square root. Pretty simple, right? So if I do that, I get X equals the square root of 7.2 times 10 to the minus 5, that's after I multiply. And then x becomes, oh, never mind, I already did. X becomes 0.00849 molar. And the importance of that in our case is that's our hydronium. So since that's the same as the amount of hydronium, the first thing you should notice, it's less than 0.1, isn't it? So that's already the first thing that's showing us the weak acid is different. It's not giving up all of its hydrogen. The actual pH in this case is taking the negative log of the hydronium. And when you do that, the pH you get is essentially 2.07. Now, that doesn't seem like a lot compared to 1, but remember, this is a power of 10 base scale to pH scale. Every time you go up by 1 pH unit, that's 10 times difference in the hydrogen concentration. So if you change by 2 pH units, that's 100 times. It's powers of 10. Now, another thing we want to ask is, what if we had solved this without the assumption? Where would that have gotten us? So I'm going to do that in red just so you can see them, a little more clearly, apart from each other. But if I had done this with a solver, I would have gotten the x to be where is it? Right. 0.00813. Okay, that's not insignificant, but it's not hugely different either. And then when you take the pH of this one, you end up getting 2.09. So here's with the assumption, here's without the assumption. They're pretty close, right? Are they close enough? Well, again, I'm going to show you a rule of thumb that kind of answers that while also teaching us something else. And that is the concept of percent ionization. So, percent ionization looks like this. You take the amount of acid that ionizes, divide it by the original concentration of the acid. So for generic purposes, when I put an HA, that's just so I can be generic. It's like the A can be any other thing that would be part of the acid. And then times 100. And to indicate this is the starting concentration, I put a little 0 in. Now, if we go from this calculation, you'll find that we can calculate the percent ionization here by taking our x, putting it over the original concentration of the acid, and then times 100. So here you get about an 8.49% of the molecules have broken down. Here's our rule of thumb. The rule of thumb is typically that we can make this assumption when we're at 5% or less. Now, you can see this is a little bit past my assumptions limit. And so we actually are detecting some difference. But even here, it's a pretty fair estimate. What I'm telling you is you're not going to have to check this. I'm pointing it out for the sake of complete, making it a complete concept. But generally, the AP exam is going to set up the problem so you can always assume this. Okay? But I know when we were doing this last time, you were saying, well, how small is small enough? This is kind of a rule of thumb we use. So when the percent ionization starts exceeding 5, subtracting or dropping the x or subtracting starts to not be as good an estimate. Yeah.
So even if you have a calculator, you should just like do the assumption?
That's an interesting question. In multiple choice, it would be interesting because if we did get the right answer and we couldn't find it, they don't let us see the multiple choice other than what I get to show you. So I've never seen that happen, but that's an interesting question. I'd say keep that in the really far back of your head in case you're like, wait, I did it the right way and I don't find the answer. You might think of it, but it shouldn't be an issue. Any other questions about what you saw? Because I have to erase this, but I'm gonna leave that side up because it's kind of the harder part, or the newer part. And then over here, I'm gonna finish the lesson by explaining something about polyprotic acids. So let's make sure this looks okay to you before I move on. Tell me the truth now. We did the first thing of equilibrium, then we did KSP, now we're doing it here. Do you see that it's about the same thing every time? Is it starting to feel like more and more reinforcement, I hope? Be honest. Or is it confusing you because it's so similar? It could go either way. I don't know. Oh, it got really quiet. Okay, that's fine. Just keep that in your
How
own.
do you know, like, the difference though? I mean, I feel like this one is just says like the pH, so you know it's talking about pH.
Yep.
But like for KSP and like the equilibrium molecule, it's like that.
Almost always, you're gonna know it's equilibrium if they show you or refer to an equilibrium constant. Or there's double arrow in the reaction. Those are clues that you can pick up right away, for sure. All right, now, the last piece is more about the reaction equations that you have to understand than anything else. So, let me talk about polyprotic acids. To do that, I'll describe ones that are also not polyprotic. Poly comes from the word in Greek for many. Protic for proton or hydrogen ion. So this is just referring to acids that have more than one hydrogen to give up. So for example, if I give you HCl, that's monoprotic because it only has one hydrogen. If I give you, for example, sulfuric acid, that one is diprotic because it has two hydrogens. And if I give you something like phosphoric acid, that one is triprotic because it has three hydrogens it can lose. So anything like this is going to be polyprotic versus monoprotic. That's all. Now, here's what's interesting about these acids. They do have more than one hydrogen to lose, but they are not equally easy to lose. And so we have to write out the expressions for hydrolysis in a little different way. Let me see if I can give you a hint by putting this table back on the board for a second. I'm just going to pull this down a little bit so we can focus on phosphoric acid. What the heck is going on here? Ka1, Ka2, Ka3, is somebody hallucinating? How'd they come up with that? What do you think that's about? Yeah?
Like, constant each hydrogen.
Very good. So what this tells us is if you look at any of these polyprotic acids, the first hydrogen is the easiest one to lose because it has the highest K value. The second one, that's like 100,000 times smaller, 5 powers of 10. The third one, even smaller. So one of the cool things about that, again, as a simplifying assumption, is that when we're looking at these polyprotic acids, the pH can be estimated just using the first ionization. Okay? What I mean by that is, yes, it's not going to give you the exact answer, but for like kind of government work, if you will, if you're doing this and you're asked to find the pH of one of these complicated ones, you just pretend the first hydrogen's the only one that matters, okay? And then you solve it like you solve it. In reality, that's not quite right, and if you're doing very delicate work, it's just a more complex system of equations you have to solve. You will not have to do it, so don't worry about it. But you will have to be able to write all of the different dissociations in sequence. So that's what I'm going to show you now. And then I'll be done. You'll be in work mode. So, for the polyprotic acid, phosphoric acid, it starts like this. Start with the original acid. You add it to one water. Equilibrium. You form one hydronium. And then you form the conjugate base of this, which is H2PO4, -1. And this will have a Ka that we label as Ka1. That's going to be the biggest one of all of them. Now, the molecule that we just produced as the conjugate base still has hydrogens. So we're going to take that same molecule and start over. Add it to another water. And finally, create a hydronium and a new conjugate base. And that's going to have a second equilibrium constant. And then, of course, this still has a hydrogen to lose. So we're going to do it one more time. What was the conjugate base on this line becomes the new acid on this line.
Wait, doesn't the H2O like
Say again? This is positive. Positive 1 though. Because these are separate molecules. I created it once here, I'm creating another one here. Right. And that's kind of how you have to visualize this. It's like a sequence. They don't all fall off at once. Otherwise, I would just write this.
Is it -1?
Mhm.
Oh, it's the same charge.
This is still -1. Oh, crap, thank you. -2. Good call, good call. But what we don't write is something like this. Because what this implies is that they all just come off at once, equally, and that's just not true. You're gonna get some percentage of these, like, significant, and then you're gonna get a tiny, tiny fraction of these doing it, and an even smaller fraction of these going through the process. But it's just understood, as you're gonna see later when we look at titration curves. I want you to be able to write these out, so you see the relationships of how each part of the titration curve fits with each part of these reactions. So we produce our final hydronium and our final conjugate base here, and obviously we cannot go any further. So just make sure you understand, if you have a polyprotic acid, how to lay out these hydrolysis reactions.
So we'll still have this even with strong acid.
The strong acids, yes, but every polyprotic except for sulfuric is essentially a weak acid. And what's interesting even about that is if we look at sulfuric acid, its first hydrogen is strong. So it'll give up all of its first hydrogens, and even its second hydrogen is not insignificant. That's why this one, that approximation that we could skip the second hydrogen, fails pretty badly. We're actually analyzing this.
So are like all the strong acids at like 100%?
Yes, for all practical purposes.
They're on
Don't make me say like points, but yes, technically we're gonna always treat them as 100%. If you guys, the bell ring, you wanna take a walk and get a break and come back, and then you can start working. If you want to, you don't have to. I'm just saying, I'm done with the lesson. Skip over your jump. I'm sorry, I didn't hear what you said.